Hello and welcome to online lecture number 13 for Chemistry 112 during the spring semester of 2020. In this lesson, we're still in chapter 17. We're going to get into some of the applications of those redox reactions we've been focused on how to balance over the last couple of lessons. If we wanted to build a battery, we can perhaps do so using redox reactions. Redox reactions are good reactions for that purpose because they involve the transfer of electrons, and we can engineer that transfer of electrons to produce electricity, which then powers our devices. But not only do we need any redox reaction, we need specifically a spontaneous redox reaction, because we want a redox reaction that will go on its own, not a non-spontaneous reaction where an only way it can go would be with outside ongoing intervention. So for example, this is a spontaneous redox reaction. Copper 2 plus ions will be reduced by elemental zinc to produce elemental copper and zinc 2 plus. So copper 2 plus is reduced, zinc is oxidized. But the reverse, elemental copper reacting with zinc 2 plus ions, is non-spontaneous. So it doesn't mean it's not going to happen, it just means it only can happen with ongoing outside intervention. And towards the end of this chapter, we'll talk about a part of electrochemistry called electrolysis, which is concerned with forcing these non-spontaneous processes to happen. But I need a spontaneous reaction. How would I be able to predict without demonstrating it or going to do an experiment whether this is the spontaneous reaction or whether this is a spontaneous reaction? Well, it turns out we can reference a table such as this one, which is called the activity series of the elements. Sometimes it's also referred to as the activity series of metals. And the idea is that this lists various elements, mostly metals, from strongly reducing, so in other words, elements that are easiest to oxidize, because remember, when a substance is oxidized, it causes the reduction of something else, to weakly reducing, which are elements that are hardest to oxidize. And the idea behind this table, this activity series, is that any element higher in this series will spontaneously reduce an ion lower in the series. So in the context that we looked at here, copper and zinc, notice that zinc is located here in the activity series. Copper is located here. So as we'd expect, and as we could demonstrate, zinc, because it's listed higher in the series, will be able to spontaneously reduce copper 2 plus ions because it's lower in the series. We'll come back to this activity series a few more times, both in this lesson and future lessons. But another important application of this activity series are the reaction of metals with acids. A very common chemical property of acids is that they do tend to react with metals to produce hydrogen gas. And we can see why that's the case, because hydrogen, compared to all these other metals, is listed fairly low on this activity series, which means any metal listed above hydrogen should be able to react with hydrogen ions from the acid, reduce hydrogen ions to produce hydrogen gas. And in turn, those elements will then be oxidized. So if we want to create a galvanic cell is sometimes referred to as a battery because it uses a spontaneous redox reaction to produce electricity. It's sometimes referred to as a battery, but technically a battery is a product that's composed of several galvanic cells. In any case, a galvanic cell uses a spontaneous redox reaction. So, for example, we could use this spontaneous redox reaction, this spontaneous transfer of electrons from zinc to the copper 2 plus to produce electricity. It's a spontaneous reaction, but in order to produce electricity, we have to physically separate the oxidation half reaction from the reduction half reaction. So we would physically separate the zinc, elemental zinc and zinc 2 plus ions from the elemental copper and copper 2 plus ions. But we will electrically connect these two half reactions. So they're physically separated, but electrically connected. So as a result then, electrons will spontaneously flow from the zinc, as zinc is oxidized, in this case to the right, to the copper, and electrons flow into the elemental copper. They're then used to reduce copper 2 plus ions into elemental copper. So we have our two half reactions. Zinc is being oxidized, and copper is being reduced. If this were the end of our galvanic cell construction, electricity would flow, but it would quickly stop flowing. Because as electrons flow, as electrons are being lost on this side, there would be an accumulation of positive charge on this side. And as electrons then pour into this side, there'd be accumulation of negative charge. So now you have a net positive charge over here, a net negative charge over here. And these electrons, which we want to flow from left to right in this picture, would quickly stop flowing in that direction and would start flowing in the opposite direction because of the positive charge over here and negative charge over here. To rectify that problem, we use what's called a salt bridge. And a salt bridge is just a device that will sort of physically connect the two half reactions, and it's composed of inert ions, inert anions and inert cations. And the idea is that as positive charge starts to accumulate on this side, these negative charge anions would begin to migrate into the solution to neutralize that excess positive charge. Likewise, on this side, as excess negative charge starts to accumulate, these positive charge ions will start to migrate into this solution to neutralize that excess negative charge. So we have several terms in regards to galvanic cells. The anode is always defined as the electrode at which oxidation occurs. And this is often referred to as the negative electrode. The cathode is the electrode at which reduction occurs. This is referred to as the positive electrode. So if we were to label this, this would have a negative potential on it, so have a positive potential on it. And then the salt bridge, it says, is typically a U-shaped tube containing inert ions. In the lab, we use something as simple as a kite string immersed in ammonium nitrate. In this galvanic cell, electrons will spontaneously flow, and they'll spontaneously flow in a particular direction. They'll always flow from the anode, where oxidation occurs, to the cathode, where reduction occurs. And the reason why the anode and cathode are called anode and cathode is because of what's happened to the salt bridge. As we referred to earlier, at the anode, positive charge will accumulate and nothing's done about it. So as a result, the anions of the salt bridge are going to flow towards the anode. Likewise, because of the accumulation of negative charge on the cathode, the cations of the salt bridge will flow towards the cathode. So the cathode and anode are called the way they are because that's the direction the respective cations and anions will flow in the salt bridge to neutralize their respective excess charges. The idea in a galvanic cell is we use a spontaneous redox reaction to produce electricity by physically separating two half reactions, but electrically connecting them. In a galvanic cell, the electrons always flow from the anode to the cathode. So if I wanted to create a new galvanic cell, if I wanted just to discuss the particulars of a galvanic cell, I could certainly draw a picture like this. But another way I can still represent the same information is with what's called a galvanic cell shorthand notation. And this shorthand notation gives us the same information that this picture does. And how we read this shorthand notation is that we always describe what's happening to the anode first. So we describe the anode half reaction first, followed by the cathode. So left to right, anode, then cathode. A single vertical line represents a phase boundary. So we have elemental solid zinc immersed into a solution of zinc 2+ ions. We have zinc solid vertical line, zinc 2+ ions, aqueous. We can also include the molarity or partial pressures of the substances as well, if needed. A double vertical line then represents the salt bridge. So we have the anode, what's occurring at the anode, a salt bridge, and then what's occurring at the cathode. And the electrons in a galvanic cell will flow from the anode to the cathode. And then if we have galvanic cells, not relevant here, we have galvanic cells, we have two substances in the same phase, we'll use a comma to denote and separate those two substances. So for example, we have this galvanic cell shown to us, and when we determine what the shorthand notation is for this cell. So we need to decide whether zinc is being oxidized at the anode and nickel is being reduced to the cathode, or whether nickel is being oxidized at the anode and zinc is being reduced to the cathode. In other words, we need to determine of these combinations of half reactions, which combination is spontaneous. And to do so, we can consult the activity series of metals or elements. We find zinc and we have nickel. Notice zinc is above nickel on this activity series, which means that zinc should be able to spontaneously reduce nickel 2+ ions and any other ions below it on this table. So we expect that the spontaneous reaction will be the one in which zinc is oxidized and nickel is reduced. So zinc is oxidized and nickel is reduced. So our shorthand notation for the cell to indicate that, we have zinc as the anode, therefore, and nickel is the cathode. To show that, would have zinc, solid, single bar, zinc 2+, aqueous, double bar, nickel 2+, aqueous, single bar, and finally nickel solid. And that'll be the shorthand notation describing this galvanic cell. And finally, our last example is looking at this depiction of a galvanic cell, and we decide whether the given shorthand notation is correct for this description. So this is showing the iron is the anode and aluminum is the cathode. But is that what we expect if this is a galvanic cell, if this involves a spontaneous redox reaction? So is the shorthand notation correct? And does that mean that iron is the anode and aluminum is cathode? Or is it the reverse should be true, where aluminum is being oxidized at the anode and iron is being reduced at the cathode? We'll decide whether this combination half reactions or this combination is spontaneous when you consult our activity series of elements. And when we do so and find aluminum and iron, notice that aluminum is above iron, which means that aluminum will spontaneously reduce iron 2+ ions, which means that the actual spontaneous reaction is the one in which aluminum is oxidized and iron is reduced. So as a result, then, this is a false statement. So the correct shorthand notation is aluminum is the anode, single bar, oxidized to aluminum 3+ ions, double bar for the salt bridge, and then iron is being reduced to the cathode, Fe2+ aqueous, single bar, and finally the iron solid electrode. So that's the true shorthand notation to describe the actual spontaneous reaction occurring in this galvanic cell. The anode's on the right-hand side and the cathode's on the left-hand side. The actual position of the anode and cathode in a picture is just arbitrary. There's no convention that the anode has to be on the left and the cathode has to be on the right. But in the shorthand notation, the anode has to be described on the left and the cathode on the right. So in the next lesson, then, we'll get into some other details about how to build a battery and then what difference does it make as to whether we do use iron or aluminum or zinc and copper as our electrodes in our galvanic cells.